Have either of y'all ever done reinforcement learning of any kind?
I mean, I've just like followed tutorials.
So idea is this: you got like a neural network, and you want to. So what does a neural network do? It's like a black box. Can't see what's inside. It's just random numbers, and you have some inputs. So you have like a vector, and this will be like your state represented somehow, and this maps into the neural network. So F, and that maps out to some other vector, and it might not be the same size. And yeah, this is like F hat is what they usually call that with a little theta, and this theta represents your weights. So you like playing tic-tac-toe or something, and so what you do is you feed in the state of the board right now, and you want to output what move that you should pick. Let's see. So this could be like just a single number, and it's 1 through 9, which picks what place in the board you want to place. And this could be like a 9 numbers, and each one's either 0, positive 1 if X is there, or negative 1 if O is there. So this is neural networks for tic-tac-toe. All right. So what you want to do is you want to say, well, the thing that controls what maps states to actions. So like, for example, if I have a tic-tac-toe board, it's like this. I'd represent this with a state vector that looks like 0, 0, 0, all the way through 9 many zeros. And then this goes into the neural network. Plug that into the neural network, and you get out some kind of number, and that'll be like somewhere between 1 and 9. So maybe 2. And then that would be like X plays at position 2. And then the state would update, and this would become 1. And then let's say another neural network, or the same neural network figures out, is given the state updated. So put in 0, 1, 0, 0. And the neural network then decides that it wants to play at position, what was that, 3, 5? And so then the state gets updated, so there's an O here, and then you have a negative 1 in the 5th entry for that guy. So you start out, and this is random numbers for your weights, because like a neural network, you just have a bunch of layers, and then you got weights for your connections between. And you want to train these so that it plays really well. So one of the ways you can do that is you build a table. Erase it.
Allowed it?
No, I can do it.
So is it typical for like each step in the environment, like you put in the state into the neural network and outputs like your like one action, or is it like it outputs like a set of actions?
Yeah. So this is one way you can do it. So you just have it output a number, and then it could output, because like usually it's going to be like decimals for your weights and stuff. So you can have it output like 2.7 or something, and then you just round it to the nearest integer and then take that. That's one option. That's not usually what people do. What people usually do is this will actually be the same size as the state for tic-tac-toe, and it'll be probabilities. And then you sample that as a probability distribution, or you take the largest number. Doesn't matter which. I think sampling usually works better. So we'll probably do it. I'm not actually going to write this as like a computer program. I have code for it already, but I'm not going to like spend time writing this thing because it's not going to help us. But just it's a nice example to get the theory down. So, how do you train this guy? So let's assume instead of having a number output, you have like a, if I feed in the neural network state vector, and the state vector I'll just draw the tic-tac-toe board. And it outputs state vector, and it's going to be a number for each of the entries. Like, it'll be like negative 2.1, 0.5, negative 0.1, something, and then you have all these other entries. And you just pick, you can sample this with a softmax, or you can just pick the largest absolute value or something. Doesn't matter. Yeah. And then you choose that as your action. So how do you actually get this to work? So one simple neural net design is like, okay, you have a bunch of inputs, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you'll have a hidden layer. So maybe there's like 4 neurons here. And then these will all feed in, so fully connected. And then this one will feed in all 4. And yeah, all the others as well. And so you'll learn a weight for each of these. So this will be like, this will be weight 1, weight 2, weight 3, weight 4. And this will be like some really large number because you went all through all these other connections too. And you'll have more layers. And these will all be fully connected, so on. And then you'll have outputs, which are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then these will all be connected to those guys. So you got to learn to weight for each of these. So what you can do is start with random weights. And the weights are a vector. And like theta is equal to a big vector. And it's like weight 1, weight 2, all the way up through weight m or something. So we'll call this theta sub I. So it starts at theta 0, which is random numbers, and then you want to update this. So we want to know what rule, how do we go from theta I to theta I plus 1?
Do you want to make it a single vector?
Sure.
The weights?
Yeah, you flatten it out. So this will be like weight n or something, and then this will be weight n plus 1. And then eventually at the end of it, you'll get weight m. So all these lines correspond to one weight, and you put them all in a single vector. That's your parameter vector. Okay. And you'll have an extra one, like you'll have a bias at every place. And the bias sits up here and feeds in all these. And then it feeds in all these. And this bias is just like positive 1.
Is this just a single number for all?
So this is 1 is what the output of that neuron is, but you learn the weights here. And these are the bias weights. So you get an extra single, for every hidden layer neuron, you get an extra 1 times a weight coming into it as well. And this is just so you can learn affine functions instead of just linear functions. You have to have this for a neural network in general.
Like my question is like, is there a unique bias for each layer, or is there a unique bias for each number?
It's for each neuron.
For each neuron. Okay.
There's really one bias, which is just the number 1, and there's a weight coming from that bias and going into each. And you can just think of this as like,
understood. Yeah.
You just add a bias number. Okay. So let's see. So the way that they do it is not to do this policy method. When I say policy, I'm saying I feed in the state, and my neural network then outputs a action distribution, and then I sample that distribution to figure out my action. So this is called the policy method. And if you learn using some kind of update rule for your weights based on a reward signal, that's called a policy iteration. So you don't actually use that in the book example. Instead, you use what's called value iteration. So instead of outputting actions, you just output a single number. So this is your output.
This is like the value network?
Yep. So the idea is you put in a state, and the network tries to say, if I'm in this state and I play according to whatever rules I'm used to playing according to. I'm expecting this expectation of reward at the end of the game. Then the way you use this, instead of just outputting actions and then picking according to the sample distribution for the policy, is you look at a board state. So at the start of the game, you have nothing, and you don't feed this to the neural network. What you say is, enumerate all the possible actions I could take from playing X. So the first action I could take is this. And then after that action, I ask, what is the expectation of reward for me? And so associated to this action, I map expected reward 1, and associated to the next action, I map an associated reward 2, and that's just, I feed this state into the neural network and it spits out a number. And that number is like R1, R2, whatever. And you do this for all the 9 actions. And so it's saying, if I look at this board, it seems like there's a expected reward of R1. And you just pick the action that maximizes the expected reward. And of course, these R1, R2 are going to mean nothing at the start because you haven't trained it at all. It's random outputs. You want to actually improve that estimation over time. So let's see. What is the update rule? So the simple version is called temporal difference 0th order. So we're not actually going to use a neural network in this case. It'll be a little simpler. You'll actually build a table. So you make a big table, which is a dictionary. So your inputs are your keys, and you have values. And you initialize them all to 0, all the values. And the keys are just the possible states of the game. So this is the empty board. This is the board where you got 1 X here. And you come up with all the possible boards you can make with X's and zeros. And you make the values all be 0. So this is like state 1, state 2. This is V state 1, V state 2, and V state 3, and so on. And the rule you use is, I should change this a little bit. I should call those S1, S2. These are just V. And these are S. I don't use it indexed and refer to them. So this is the setup used, and you just want to improve these numbers so that they're accurate guesses for like what the value should be. So that when you maximize the expected value, you play in a good way. So the way you update that is you play a game, 1 game. So we're going to do the following. I start with this. I'm going to play X. You're going to play O. I look at all the possible outcomes or the possible actions I can take. There's 9 of them. And right now, I don't know anything about the rewards, and they're all 0 expected. So I look at all these actions I can take. I consider the after state of playing each action. And then I maximize the reward I can expect, and I just pick the first one if there's a bunch of ties for maximum. The first one's out. Okay? So I then hand the game over to you, and you make an update.
Oh, middle.
Okay. So now I don't know anything. And just before that, before you had played, let's see. That's correct. So you made that, and the game's handed back over to me. So I'm going to call S1 this state, empty board. S2 is going to be Let's see. Did I skip one? S1, S2 are supposed to be. I play the first move. Then S3 is Vijay plays O in the center. And then S4 is whatever I end up choosing for the next state. And it's clear that the one I'm going to choose next is just X here, because that's the first thing. I don't have any values figured out. And then Vijay will pick something next. But before that, what we'll do is when I make a step or when I make an action, I'm actually going to update my value function. And so the way I do that is by this rule. V of st, so the value ascribed to whatever state, is going to be updated, and it's going to be itself plus some change. So plus alpha, and then I think it's the difference in the current state and the last state's value. The st. That's the update rule. And this is just the learning rate parameter, so it's something positive. And the idea is you want to take whatever the value at the next state is, and you want to adjust VST, which is the previous state, or the current state, in that direction. So if alpha were 1, you would literally just replace VST with VST plus 1. So this is the temporal difference, 0th order update rule. So you usually use like alpha equals 1 e negative 3 or negative 4 or something like that. It's more in that range. And that's just 10 to the negative third. So you'll actually do that update rule at every step where you take an action. And in fact, at every step actually. And I think you don't do the ones like this. So this would actually be S2. So whenever I make a move, I also let Vijay make a move. And then whatever happens then, I consider that to be the next state.
Oh, yeah. The V of ST and all of them are just the expectation distributions?
So it's a table. So it has no real meaning until I try to, like, so the way they derive this rule is by thinking of it as expectations and then saying eventually it will converge to the true expectations. But yeah, this is a convergent recurrence relation that lets you update until you converge to the expectations. And it will, just by theoretic considerations. So that's S2. So what I do is I go down to S1 and I say I want to update the value for this. And whatever the value is for this, I take the difference in the two and I update in the direction of S2 by some multiple of the difference. So it turns out that in this game it won't change at all because I don't actually see any reward. That'd be clear right at the end what that means. So now I make another move. I choose this. I have to because that's my policy. I maximize the value. And then Vijay makes a move.
Top right.
Okay. So S3 is going to be this guy. Okay. And then I do my update rules or update the value of S2. Then I make a move, and it's going to be this one. And Vijay plays a move.
And bottom left.
Yep. And Vijay wins, and the game ends. That's a tic-tac-toe. Or excuse me, that's a 3 in a row. And so the game ends. Now, I do not update this by using V of S4. So the rule here is if you only see rewards at the end of the game, you can use this rule. You have to change it a little bit if you can see rewards earlier in the game. And so what I do is I want to update VS3. And normally I would just do VS3 plus alpha times VS4 minus VS3. So actually you do end up using this rule. It's just, this is something where I know the true value. I've actually measured it. So I can go ahead and fill in my table with this when I observe the reward, because it's the last one I'm going to see in the episode. So I just fill in that with whatever the reward is. So I lost, so I get a -1, let's say. So this is actually a -1.
This is on policy.
Sorry?
Online.
This is, you can do this online or offline. And if you do it online, it just means when you deploy, you keep training. So this method allows online training. And I got like this demo Jupyter notebook where you can like play against it, and it actually learns. Firstly, it'll self-play, so it plays perfectly, and it'll get draws. But then you play against it, and it just keeps getting draws. But if you're kind of dumb and you don't know how to play tic-tac-toe perfectly, then it will actually learn to beat you and not just get draws. So it'll practice against you as you play it. Yeah, so VS3 then gets updated with this -1. But none of these get updated. So we didn't learn anything about the start of the game from this. So the next time you play, what's going to happen is it's going to play out the same way for the first few moves. This is going to go to this, assuming Vijay plays the same way. And I don't know anything about moves I can make. Like I could make this, I could make this. These all have the same after state expectation of reward. Let's see. I think I do actually need the intermediaries, right? Like the ones where I just played and VJ hasn't played yet. So just assume you stuff those in. But I haven't learned anything up to this point, so I still make this move and end up here. And then once I'm here, I learned, I should update this a little bit. So this is actually S5. And then I've got S4, which are the after states of my own moves. So X, X, O, O, and then will have played this way. Mm-hmm. And when I do the update rule at the end of the game after VJ plays and wins, I will back propagate the update to S4. These really should be higher numbers, but kind of messed up, so don't worry about it. So this will have a slightly negative value, which is going to be alpha times whatever -1 is, so negative alpha. So VS4 is negative alpha at this point. So now I won't choose this anymore because that's negative alpha, and the other ones are all 0. So I'll actually go to this instead. And then VJ will win, and I won't play that anymore. And then the next game, let's see. So I didn't play this, so the reward of this state doesn't back propagate up to S3. So I don't learn anything until I figure out a good policy or I've exhausted everything. So I play that, it's bad. I then play this, and then VJ has to pick a different move. And if he picks this, I end up playing this. But you just keep going, and you keep playing down the paths until the reward expectations propagate back up to the starting state, and you learn a good policy. So that's all you have to do. You just use this update rule or whatever. So that's temporal difference learning. Very simple. It's just this update rule and nothing else. The trouble is, this is really expensive because you have to keep that big table of all states and the value for each. So you can't do that with rockets because you can't memorize all the states. Infinite many. Okay. So that's called tabular reinforcement learning.
When you back propagate the values, how does the weights get affected in that?
So the weights in that case are the values. So there's no neural network. All right. All I have that I learn a policy from is my states and my values. So this one will have like 0 to start with. This one will have 0 to start with, and so on. And then I update these based on the back propagation. Or bootstrapping, they call it.
So even to start this, you have to have an exhaustive set of all states, right?
That's right. And what you can do is you can make a dictionary, and every time you observe a state, you add it to the state collection, and you'll have a value associated to that state. And you only populate this once you actually see a particular state. And if you do that, then you only have to keep track of the possible states. So it's a little cheaper. And I think that's how I do it in the Jupyter notebook.
That was pretty good.
Yeah. But it when that came out, it actually was the best backgammon player at the time. It was Superhuman. And
What was it?
Backgammon. So that I forget what the game was like, what the RL engine was called, but at the time that was like the first big success of reinforcement learning. And it said, okay, everybody needs to try doing this for chess too, like all these other games. But it was Superhuman, and nobody could beat it. Yeah. So with neural networks, same idea. You have a neural network and it has weights, a weight vector theta, and it'll be theta I, so you'll update it. You'll change your weights and it'll increment I. So you have a starting weight of theta 0, theta 1 after that, theta 2 after you do another update, and so on. So the update rule using the reinforce algorithm, this is reinforce. This is actually going to be not a value method, a value iteration, but it's actually going to be a policy gradient method. So your neural network is going to eat states. I should say all the different ways we could do reinforcement learning. So one is states mapped into the neural network, and they get sent out, and you get outputs which are value functions. So this is value learning. This is value iteration. There are Q-learning algorithms. And so what you do with the value learning is you do the same thing we did with tic-tac-toe, where you look at all the actions you can make, consider the after states, plug them into your value function, and try to maximize the value function. So Q-learning is you map states and actions in, and you spit out what's called the Q value. So Q is just a function that eats a state and an action and spits out a value expectation. And it's very much like this. It's just that you can also plug in action, and that way you don't have to make code for saying, if I do an action, here's the after state I can expect. It's just that the neural network actually learns directly from the state and action to predict the reward. So like in tic-tac-toe, the way this would work is value iteration. I just plug in the state, and I think about, so I plug in the state of the after state of an action, and then I figure out the value of that. But if you have a game where you can't do that, like you can't say an action produces a particular state ahead of time, like you can't model it perfectly, you can't do that. So what you would do in Q-learning for tic-tac-toe is you would say, instead at the start of thinking of all the actions I can take, like I take this action and I plug this into value function, you don't do that at all. What you do instead is you plug into your Q function the current state, which is nothing on the board, and you put in X here. So that's your action. And what I mean with this notation is that I'm not saying this is a state, I'm just saying this is the first action. So I could write 1 if I wanted to, or A1. And this will spit out the same thing that the value function would have spat out if I put an X here for the state. And then you try to learn what this Q function ought to be, and that's a neural network usually. You can also make it a table method where you store these pairs of states and actions, and you store the Q value for each one. So it doesn't have to be a neural network. Another is, let's see, policy methods of the iteration. And here you take states and they get mapped directly to actions, an action distribution, or people will write pi here. So this isn't just a particular action you'll take, it's actually a distribution of probability values over all the possible actions. And you try to learn this neural network weight configuration vector. So that's all the methods. So reinforce is a policy iteration method. So you actually do this. Okay. So, how do you go from here to here? Reinforce does the following. It says, I'm going to use t instead of I. It says theta t plus 1 gets assigned to be theta t plus gt, and then it's this funny little thing, a gradient of, so this is a vector, pi, and you plug in at given st theta t over, what is it? Same thing, just not with a gradient. That's update rule. So what is this? This is the this is the return over the whole, okay, let me put it this way. You have a bunch of times in your simulation that you're doing over the episode. T equals 1, 2, so on up through n. And the idea is you get a reward at each of these. So you get R1, R2, up through Rn. And these are all real numbers. And so you define G1 to be the sum of all these. So GT in general is you look at RT and then you add that to RT plus 1 plus, and then you go all the way up to Rn. So it's the remaining reward after time t. This is the return at time t. Not the expected return, but the observed return after time t. Yeah, so let's see. So
can you repeat how you define the return?
Yeah. So if you play tic-tac-toe, you get rewards at every step, which are 0, and then at the end you get either a -1, a +1, or 0 if you get a draw. And so Rn in all those cases is either -1, +1, or 0 for the end state reward, and then the rest are 0.
You just need raw reward.
Yeah, I don't get any reward for all these R's. So that's the reward, but the return is different. It's the sum of all the remaining rewards. So what you do is you run a whole game of tic-tac-toe and play it according to your policy network, and it'll pick actions for you. And you just say, okay, keep a track of what rewards I saw at every time point, and call those R1 through Rn, and then figure out what all these returns are, GT. And so G1 will be the sum of all the rewards. G2 will be sum of all the rewards except R1, and so on. So those are the returns, the truncated returns. And I use that in my update step for the weights. So let's see.
This is for a single episode or like
Yes.
exhaustive?
Yeah. So it's one episode. So this is like a stochastic gradient descent on episodes, your training examples. With temporal difference learning, you can do it online, so you actually learn during the game. But with reinforce, you cannot learn during the game. You have to do a full episode. So this actually works for rocketry because in your simulation, you can run one flight. And then when you run out of fuel, the episode has to end. So you have the ability to do these episodic rewards. So let's see, what is theta sub t? Why is there time associated to that? Okay. So the schematic for doing reinforce looks like this. Step 1, run an episode. With current weights. So theta is sub-0. Okay? And you collect a couple things. You collect and you remember your rewards that you observe over the episode. You need some other things. You remember what states and actions you saw at every time. S1 through Sn, so all the states you came across. You collect all of the actions that you took. And you don't actually have to do this because you get these actions by sampling your probability, your policy distribution, which is what your neural network is outputting. So I'll explain what this is in just a second. But you can collect all your actions that you took at every time step. And what else do you have here? That's accounted for, that's accounted for, that's accounted for. And I'm wondering why this is updating with the time, because that's strange. Because what I do is I run the whole episode with just theta 0 for my policy. Okay. It's a little bit funny, but it works. So these are the 3 things you collect, SAR. And then after you run the episode, go over all timestamps, or time points. So t equals 1 up through n. And when you go over each one, you do the following. You want to run this update rule, but you need to calculate this right-hand side first. So what you do is you say, calculate GT, which is the sum from I equals T to capital N of Ri. So it's all the remaining rewards. You need to calculate this guy. So you have saved your AT and your ST. And you've saved theta 0. So you know what your weights were at the start. So what it means to calculate this is the most complicated part of this thing. So pi is a neural network, and it has weights theta 0 right now. And so, let's see. I really need to do t minus 1 here. And, I should call this theta 1 actually. So we'll just make this that. Okay. So you start with the initial weights, theta 1. And this pi is like, it's saying, what is the policy distribution for the state that you're in at time t? So like time 1, you'll look at the first state you saw in the episode, and you'll ask, okay, well, I take my original weights that I had during the episode, and I calculate what the policy output of this is. And what that's going to look like is like the neural network will spit out a vector, and it's going to be a bunch of probabilities. And you remember what you took for A1, which was your action. And so you just look at the particular one that is associated to that particular probability associated with the action that you actually did take. And you ask what that probability is. And that's what this number is. Okay, so that's literally just this. And this only happens the first time step. So that's what pi A1 given S1 and theta 1 vector is, this number. So you calculate that guy. And then you calculate the gradient. So that's nabla pi AT ST theta T. So what this is you have a neural network, and it's like these are the outputs, and you have a bunch of inputs, which is your state. This is ST, and this is the pi, and we'll just call this AT given ST. So for time 1, we'll just look at time 1. You'll look at the action you actually took, and you will differentiate that number with respect to all the weights. And that will create a big vector. And it's not with respect to the state, it's actually with respect to the weights in here. So this number depends on these guys by some mathematical formulas, some linear combinations and activation functions. And so you differentiate whatever the formula is for giving you this guy in terms of these guys. Now JAX can handle this automatically with autograph, so you don't actually have to do this by hand. And I think the tree utils library in JAX is what you use to do this really fast. So it's easy. So you actually differentiate the probability of the action that you did take with respect to each of the weights. And then that is your gradient. You form that vector. Okay. So that's all the hard stuff. But you have to come back for the second time and all the others and do something different. And then finally, you do the update rule. All that stuff. So you've calculated everything in there, and you're good to go. You already know theta 1, you know G1, you know these two, and you can just update to get theta 2. Then when you want to go to the next data in this loop, you go to theta t equals 2, and things change a little bit. This is really easy. It's just the same thing without the R1. You go here, and it's a little bit different. So what we did here was we wanted to say, well, we took a particular action, so you can look at like what the probability distribution was by plugging in the state into your neural network, seeing what the numbers that come out are, and then looking at the number that's associated to the action that you did take. The thing is, though, you don't actually want to get the same numbers out here that you got when you did it for t equals 1, or even that you saw in the episode. So this has nothing to do with what was in the episode for your neural network output. You still look at the same action, so the same row in this vector, but you will update the weights for your neural network to be theta 1, or theta 2 this time instead of theta 1. And so you get different numbers out this time. So this number actually comes out different. Even if the action is the same, and the action could be totally different action, so you might pick a different row this time. And the state could be totally different. But if there's A2 and S2 are the same thing as A1 and S1, you still get different numbers because theta 1 is not theta 2. And then you do the same thing here. You do that gradient calculation, and you just differentiate with respect to the weights. And you will actually get the same thing for this gradient. because the gradient doesn't depend on the weights. It's just a derivative. So it's like if you change the weights a little bit, you would get this gradient. Like it would move by this gradient. The pi would. So this you can pre-calculate ahead of time for each AT and ST. But you don't really save anything because you only end up updating this one time for a particular AT, ST. It doesn't really save anything. But you don't need to, you don't end up actually changing the weights here.
Well, grading kind of does depend on the weights. Like not for the last layer.
So you have, let's say you got F of X.
But this is like chain rule, right? Like it is.
It is.
Not, yeah, it is chain rule.
Is that right? You will, won't you? Okay. So if you only have, you're right. The last layer doesn't care.
Yeah.
So, but the rest does. But AutoGrad will handle that, and you do have to stub in this theta t update. It's a theta 2 in this case. So you're right. It does matter. Okay. Good. All right. So that is it, and you just do that for all the time steps, and then you have your update, and you're ready to run another episode. And assuming your
So there will be like theta, or there will be like n updates.
Yeah, there will be for one episode. So there needs to be a learning rate parameter here. So you choose something ahead of time. So yeah, assuming your learning rate is picked right, you should perform better on the next episode. So that's how this works. So this is a reinforced algorithm. You can actually use this to fly a rocket. People don't usually use this by itself, though. There is a improvement to it called reinforced with baseline, but we won't worry about that because it takes longer to code right now. So the update rule for reinforced with baseline looks like it's going to be theta t plus 1 gets updated to be theta t plus some adjustment. And then adjustment is going to be alpha times, and you just change this return. So you keep the return, but then you subtract away something, which is b st. And then the rest is the same. So you just introduce this guy. So what is b?
Oh, like a discount factor.
It is a reference function. You can use value estimations, I think. Like you can let b be some kind of value function and then train that separately, but you don't have to. It says you can use any arbitrary function. Where does it say what b needs to be here? Yeah, so they do, in the book, they give you an algorithm for making b be a learned value function, and they give you an optimized computation for it, but you can just check the book if you actually want to program that. It's literally this, and to calculate b, you just use this delta thing, and delta ends up being g minus b, and so that formula is all you end up using, and so you have to know what this v hat thing is, and that is a differentiable state value function parameterization. So it's state value, which is a value function. And then you update the weights W for V every step. And so these two rules give you the updates for that. That's all you have to do. It's just a gradient update again. It's very easy. Yeah, it's in the textbook if you need it.
Do you have the intuition like how reducing this value like affects?
Yeah. So, okay. Assume this is your value function. So it's an estimate of what you expect the return to be.
Okay.
And so if there's any error between this and the true return, then either the returns have variance or you just have bad estimates of the return. So if you can think of this as an error number in your estimation for the value.
Yeah.
And so, or for the returns. So if this error is large, you'll do a bigger update to your policy.
Okay.
So it's trying to push you out of places where you can't make good predictions about the values that you're supposed to expect. So you don't end up doing policies that are unpredictable on returns. That's the idea. Tries to make
But B is not the value function, right?
It can be chosen to be anything, and the best choice is typically a value function.
The same value function that's like the main value function.
So we don't have a value function in the rest of this.
Yeah.
So introducing it helps you learn faster. So yeah, you'll use a neural network for it, and it eats the state and it spits out a number.
Would be like be thought of as like a critic then?
Yeah,
That's kind of what I was asking.
Critics usually are Q functions. So they will critique the actions that the policy network is taking. But this is just critiquing the states that you get into. So people don't call it a critic method just because it isn't in line with the typical design of the algorithm. But yeah, they have like a picture here of reinforce learning. And then here's difference in the convergence for reinforce and reinforce with baseline. So baseline improves the learning a lot. This is the reward you get, so higher is better. This is training time. And I saw it made carpool perform a lot faster when I did it. So that's the trick that you do. And these are policy gradient methods. You're actually calculating the gradient of the policy distribution. That's why it's called that. So I think all the stuff we do for rockets probably will be policy gradient instead of active critic.
Right.
Just because it is good at fine-tuned control of like motor function and stuff. Okay.
Should we, for that project, should we generate the actual actuator values, or should we generate the angles and then do the control stuff?
Actuator values. It depends. So I was talking to Jack about this, and he was like saying this kind of obvious thing, which was you don't want to have it output controls for the actuators so that you're like flip-flopping back and forth and doing like bang-bang policies. So you need to put some constraints so you don't like flip too hard or change things too hard. So what you're saying about just making it output the targets is good, because then you can just manually control whatever the actual control is. So if you want to do that, that's fine.
But we're going to have to put that behavior in the simulation itself, right?
Right.
Yep.
I would just write like a big class that lets you change the properties for the class or for the objects instantiated from that class, and then have the properties be like, okay, this is the rate of change for whatever.
So for the simulation environment, we're going to have actuator simulation. Given the values, given for example a certain theta, there's going to be some response delay, and there's going to be some speed limit that you cannot have an angular rate greater than this.
Yeah.
These two things.
Yeah. That sounds right. Sounds physically accurate. So that works, and you want to actually use that in your. You probably, if you put this on a real rocket, you probably want to write some interface layer like that too.
Right.
Because otherwise it's going to give just like crazy control values and maybe fuck the rocket
Yeah, how hard is it to like actually make like a good reward function?
Okay, so I think if y'all have time, we'll actually code something. But
I have to go.
Okay.
My class started like 30 minutes.
oh shit. Let me end this.